Welcome to solverfy.
So here we know that for part A, the angular wave number in region 1, we can say K in region 1, this would be equal to 2 pi over the wavelength. This would be equal to 2 pi divided by Planck's constant divided by the momentum. And so this would be equal to 2 pi times the momentum divided by the Planck's constant. This is going to be equal to 2 pi times the mass times the velocity divided by Planck's constant, and now we can solve. So this would be 2 pi multiplied by the mass of the electron, 9.11 times 10 to the negative 31st kilograms, multiplied by the velocity of the electron, 1.60 times 10 to the 7th meters per second. And this would be all divided by Planck's constant, we know to be 6.626 times 10 to the negative 34th joules second, and we find the wave number to be 1.38 times 10 to the 11th per meter, or meter to the negative first. This would be the answer to part A. To part B, the energy of the electron in region 1, we can say energy in region 1. So the energy in region 1 would be equal to the kinetic energy in region 1, and this would simply be equal to 1/2 mv squared. This is going to be equal to 1/2 times the mass of the electron, 9.11 times 10 to the negative 31st kilograms. And then this would be multiplied by the velocity of 1.60 times 10 to the 7th meters per second quantity squared. And so we find that the energy in region 1 is going to be equal to 1.17 times 10 to the negative 16th joules, or we can say 728.8 electron volts. Now here in region 2, where the electric potential V is equaling negative 500 volts, we can then say the kinetic energy of the electron in region 2 would be equal to the energy in region 1 minus the potential energy sub B. So this would be equal to 728.8 electron volts minus 500 volts, or 500 electron volts rather. This would be equal to 228.8 electron volts. This would be the energy in region 2. And then continuing on part B, we find that the corresponding angular wave number in region 2 would be equal to 2 pi over h multiplied by the square root of 2m multiplied by the energy minus the potential energy after going through that electric potential. Now we can say that this is going to be equal to 2 pi over h times the square root of 2m times the kinetic energy in region 2, and we can solve. K sub B would be equal to 2 pi divided by 6.626 times 10 to the negative 34th joules second, and this would be multiplied by the square root of 2 times 9.11 times 10 to the negative 31st kilograms, multiplied by 228.8 electron volts, and then this would be multiplied by essentially 1.6 times 10 to the negative 19th joules per electron volt. So we need to convert to joules, and this would be the square root of the entire thing. So the kinetic energy, sorry, my apologies, the wave number, lowercase k, in region 2 would be 7.74 times 10 to the 10th per meter, or meter to the negative first. This would be your answer to part B. To part C now, we know that the wave functions in the two regions can be written. We can say lowercase psi sub 1 of x would be equal to aeikx plus be negative ikx. And we can say in region 2 This would be equal to C E I K sub B x. And we're going to match the boundary conditions. This leads to A plus B equaling C, and AK minus BK equaling CK sub B. And solving for B and C in terms of A, we can then say B over A is going to be equal to 1 minus K sub B divided by K divided by 1 plus K sub B over K. And we can then say C over A. This is equaling 2 divided by 1 plus K sub B over K. And knowing that K sub B divided by K, this is equaling 7.74 times 10 to the 10th, and then divided by 1.38 times 10 to the 11th. This is equaling 0.56. So essentially we can find the reflection coefficient for part C, R. The reflection coefficient would be absolute value of B squared divided by A squared, and this would be equal to 1 minus K sub B divided by K divided by 1 plus K sub B divided by K quantity squared. This is equaling 1 minus 0.56 divided by 1 plus 0.56 quantity squared, and we find that the reflection coefficient is 0.0794. This would be our answer for part C. For part D, now we want the number. We know the number of electrons in the incident beam, so this would be 3.00 times 10 to the 9th electrons. Again, electrons in the incident beam. So we can find the number reflected. The number of the reflected electrons would be equal to the original number of electrons in the incident beam multiplied by the reflection constant. So this would be reflection coefficient. So this would be equal to 0.0794 divided by 3.00 times 10 to the 9th electrons. And we have the number of electrons being reflected equaling 2.38 times 10 to the 8th electrons. This would be our answer to part D. That is the end of the solution. Thank you.